happens then when we don't know the time. This is useful when the time interval, this is your blank on your little handout, time interval is not known. So my third one, so my first one was when my displacement was not known. My second one was when an actual position, like a final position, is not known. And my third one is when my time is not known, when my time is not known. So let's walk through how we get this. How do we get the first time? We're going to go back to our acceleration. Our acceleration looks like this. All right? What would I do to get time by itself? Change in time by itself? Yeah, you can multiply both sides by that change in time. And then we need to divide both sides by what? By the acceleration, right? You don't have to write this part down, but you do probably want this one. Acceleration yields this one. This is the one that's the first one on there. Change in time, then. Change in time is the same thing as your final velocity minus your initial velocity divided by your acceleration, your average acceleration. And so that's one thing you can do to find time. If you have your velocities, your two velocities and your acceleration, you can find time that way. All right. And then we're going to look at one of our change in x's. So one of our displacement ones looked like this. This was one of them. So that next little block, go ahead and write him down. This was one of them from the very beginning. Remember, our first rule, our first equation was if you need your displacement, you can say 1/2 your final velocity plus your initial times your time. Okay? However, we no longer know time. This one's going to help us find our time, right? And so one of the things that we can do is we can take this right here, assuming we don't know time, and we can replace time with it, right? We just said change in time is my final minus my initial velocity over acceleration. So let's replace that time with this. Replace that time with this, all right? Looks like that. I just put it over 2, by the way. So this whole group over 2 times what I replaced this with, all right? So I took this equation, I replaced my change in time with it. I just substituted. Now this looks hideous, by the way. This does not look good at all. So we're going to make this look a little bit more simple. Side note, hopefully you remember this. What happens when I multiply something like this? What happens when I multiply something like that? I FOIL it. What happens? It's a special case. It's a squared minus b squared. My middle term cancels out. It's a special case, right? Multiplying conjugates. What do you notice about the numerators here? They're conjugates of each other, right? So what do you think would happen if I multiplied those two fractions? I would get the first one squared minus the second one squared, right? And on the bottom, I would just have 2 times my acceleration. Everybody see that? Yes? No? I promise that's what happens, but you can FOIL it. We'll look at it. You're just multiplying your numerators and your denominators. So if I take this, if I were to multiply v of f times v of f, I get v of f squared, right? If I multiply v of f times negative v of I get a positive v of f, v of I. Plus, if I multiply these two, I get a positive v of f, v of I, right? And if I multiply the last one, I get vi squared. What happens to my middle terms there? They cancel. So I end up with my initial velocity, my final velocity squared minus my initial velocity squared over 2 times my acceleration. And that's how you can find displacement and you don't even have time in there. There is no time in that equation. So this is trying to find your displacement when your time is unknown. All right. Remember that long one we just did? We just did the long one. X final was my initial plus. I had basically my change in X, right? It's my initial plus my change in X, right? To find your final, where you started plus your change in position, right? Well, now I've just redefined my change in position, correct? So there's yet one more way you can find your final position. This time, what if you don't have time? You can just replace him, and that's where we get this equation from. Let's say I don't have time, right? I can't use my original one that I just had. I can now replace this with this one that I just found, the change in position when I don't have time involved, So the summary, we have 3 equations of motion. The first one is to help you find your final position. So you need your initial position, you need your acceleration, you need your change in time. All right, so this is what we ended with when we went through all the different steps to derive this particular equation. This is what you need for your final. The second equation is when you're trying to find displacement or position, and there are 2 options there for that one. And then the third equation is when you don't know your time, okay? So when you don't know your time. So it just depends on what you're trying to find in all of this. If you're trying to find velocity, if you're trying to find position or displacement, or if you're trying to find position or displacement without time. Those are the 3 things that these equations will help you with. All right, so this example says a train is traveling at 26.8 meters per second, slows at a constant acceleration of 0.500 meters per second squared. How far does the train travel until it comes to a stop? How far does it travel until it comes to a stop? All right, so let's talk about what we know. Traveling at a rate of 26.8 meters per second. What is that? What is that telling us? This is the starting velocity. It is telling you how fast it is traveling, right? Starting velocity. It slows at a constant acceleration. That's pretty obvious what it's telling us there. Acceleration of 0.500 meters per second squared. By the way, anytime you see meters per second squared, that's going to be a clue that it's acceleration. Meters per second is going to be a clue that it's velocity. So yes, it is very important that you notice it said slow when we start to put those down. All right, how far does it travel until it comes to a stop? That word stop is actually telling us something. What is that telling us? So we have initial velocity. That is going to be 26.8 meters per second. We have final velocity. That is 0.0 meters per second. And by the way, when you're thinking significant digits, 0 is not technically a measurement, so you don't have to count that as part of your measured significant digits. So when you see zeros, you're not going to be like, oh, well, they only wrote 0.0. That's only 2. There are no significant digits actually in that 0.0. All right, so you don't count that for significant digits. We also know our acceleration. All right, our average acceleration here is what they're giving us. And yes, it is a negative because they said that it slowed at a constant acceleration of negative. So we're going to say negative 0.500 meters per second squared. What you'll notice is that we do not know time here. We are going to use the third equation because we really don't know anything else about it to plug in, but we have the final velocity, we have the initial velocity, we have the average acceleration, don't we? And so now we're just going to plug those in, all right? The final matters. I know it's 0, but the final matters because you're subtracting, okay? If my initial velocity was 0 and I was subtracting a 0, that really wouldn't matter. But because I'm subtracting from 0, it actually matters here. So when I plug this in, I'm going to say 0. Of course, the square doesn't really matter, but technically it's squared. Minus my 26.8 squared over 2 times my negative 0.500. All right. So when we do that in your calculators. You're going to get a rather large number, not too bad. We should have gotten 718.24 meters. Yes, hopefully meters. So let's look at our, this is actually meters per second. So when we square it, you get meters squared and seconds squared. Down here, you get meters per second squared. I'm just showing you why you can check your units. The second squares will cancel. One of the meters will cancel, and you're going to be left with meters, by the way. So that's why that works. Now let's talk about significant digits here. Significant digits of the measured. Remember, 0 is not considered a measured. How many significant digits do we have here? 3. How many do we have here? 3. What should my answer be? 3. So when I have something like this, I count from left back. All right. So I'm going to say 718. I'm going to round this to 3 significant digits. So this is going to be 718 meters because 3 significant digits is what you need. It's saying how far, right? So a distance per a time is going to be movement. So velocity is going to be meters per second, or speed, depending on which one you're talking about. Acceleration, meters per second squared. But if I gave you just a straight up distance, I would say I walked 3 meters to get to you. And so there is no per time if you're not talking about the rate of movement. You're just talking about the displacement, how far it went. All right, so if you had wanted to use the second one, you would have to calculate time first. So if you wanted to figure out your change in time, you're going to say, well, my final velocity minus my initial velocity divided by my constant acceleration, all right, is going to equal my time. So you should get 53.6 seconds there, all right? Now, if I were doing this, I would go straight to the equation with what I had, right? And I wouldn't try to calculate time and then go to the second equation and plug in time with all of those other things. I would go straight to this one because this one's easier with the information I've been given. But you could. If they said how long did it take, you could then answer that question as well. Here. Free fall, uniformly accelerated motion. This is based off of gravity. We are using the gravitational pull based on meters per second squared. If I said meters per second squared, what is that representing? Those units tell you it is what? Acceleration. So 9.81 meters per second squared. You'll often see it 9.8. And if you're just trying to estimate in your head, you can estimate at 10 and you'll be pretty close. If you're just trying to, hey, does this make sense? Answer. You could estimate it at 10 meters per second squared. You'll notice it says downward. So in an algebraic sense, when I say downward, I'm going to use negative 9.81 meters per second squared. All right. This is specifically on the Earth. Okay. This is specifically on the Earth. Gravitational pull on the Earth. Okay. If we were somewhere else, that is a different gravitational pull depending on the mass of what you're on. We'll also point out that for all of these examples that we're going to do, wind resistance is not going to be something that we take into consideration. You do have what's called a terminal velocity. So terminal velocity is that if you were to have a falling object, you have naturally wind resistance that pushes against it, right? So if something is falling, it doesn't just keep accelerating and keep accelerating. It is going to reach an equilibrium point with what's pushing up against it. And that's as fast as it's going to be able to fall. That's called a terminal velocity. All right. It doesn't mean it's the velocity at which you stop. It means it's the velocity at which you stop increasing, accelerating. Okay. And so if you were to drop something off of a really tall building, it would get to its terminal velocity and it would maintain that velocity. And you can see it. They've done experiments with like light blinking to catch it, and you'll see the acceleration go fast, 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 and then you'll see it space out and become constant, right? Because it reaches a terminal velocity based on wind resistance. But what we're doing with the questions that we have here, we're going to kind of exclude wind resistance and assume that there is no wind resistance on the object as it's falling. all right? Even though, and different objects will have different terminal velocities. It depends on the shape, the size, the mass, etc. of the object. So now we're going to take those three equations that we had, and instead of acceleration, our acceleration is going to be the same thing. Our acceleration is going to be gravity. And so if we look at that first equation, final velocity, we're going to say initial velocity plus gravity times time, because gravity is our acceleration here, right? So we have an initial velocity. Let's say we chunk that ball off the bridge, right? But the acceleration of that ball, because it is not powered by anything else except gravity, is going to be gravity. If we look at our second equation, now this has a change in y, and I'm going to tell you why it has a change in y. You are welcome to leave it as x, because I feel like we've been using x over and over for it. The reason is because when we're talking about gravity, it's constantly moving up or down on the y-axis, right? Whereas other motion, like a train moving, can be moving this direction, right? We don't really have an axis, so to speak, but gravity does have an axis. Gravity's pulling down, if you were thinking about that. But you're welcome to leave it as change in x, and in my brain, I left it as change in x because that's what all the other ones were. Our third equation, again, this is going to be your change in x that we're talking about here. And we just replace 2a at the bottom with 2g, gravitational pull. And so these are identical to the ones we just did with acceleration, except now our acceleration is straight gravity because these are free falling. This is only for objects that do not have any other source of power. So like a rocket ship, right, when it is going off the planet, our acceleration is different than when something is falling. Falling is always a gravitational acceleration. A stone falls from a bridge high above a river, ignoring air resistance. What is the stone's velocity after 4 seconds? Velocity after 4 seconds. So we need final velocity. So we're searching for that. We are looking for final velocity. We need to plug in what we know. Initial velocity. A stone falls. What is its initial velocity? 0. Nobody threw it, correct? So 0. And then we are going to add to it. What does G stand for? Negative 9.81 meters per second squared. And we are going to multiply that by 4 seconds. Question. So in this problem, again, I'm gonna hone in on how we do these units, because units are something that people struggle with. Seconds are in the bottom here squared, and they're in the numerator on that 4 seconds. So those will cancel, and I'll get meters per second. What is meters per second? Velocity, which is what they asked me about, correct? They asked me, what is the stone's velocity? So I'm just going to multiply. When I multiply, what do I get? I get negative 39.24. All right, let's look at our original problem. What did they measure? 2 significant digits is what they measured. 2 significant digits is what they measured. I need 2 significant digits here. So how am I going to do this? Negative 39 meters per second is my velocity after 4 seconds. Something is falling, your velocity is going to be negative, right? Does that make sense? The other thing is a quick and easy rounding of gravity is a 10, negative 10. So negative 10 for 4 seconds is approximately negative 40. Does negative 39 make sense? Yes, it does. So do you see how I did that as a quick, does my answer make sense? 10 is a rounding of gravity. Negative 10 is rounding. We're not going to round that much. But if you did, you could do a quick check. I fell at negative 10 meters per second squared for 4 seconds, approximately negative 40 meters per second, right? And so a negative 10 is an approximation of gravity, and you can see if your answer makes sense. Negative 10 for 4 seconds, negative 40 makes sense. Negative 39 then makes sense when I did it exactly. All right, so A was asking for final velocity. How far, what does that want me to tell them? Distance, displacement, yes. So I'm going to use my displacement. I'm going to use my displacement, one of my displacements. So change in x. That's what we're trying to do here. We're going to say initial velocity, it fell, 0, times how long it fell, 4 seconds, right? We're going to add to that, and yes, in your calculator, you can just put 0.5, that's 1/2. Gravity, that's negative 9.81 meters per second squared, times our time squared, 4 seconds squared. Okay, 4 seconds squared. So units, good question on units. I have seconds squared here, and it's going to count out with seconds squared there. So I'm going to end up with meters, which is how far, right? When you do this, you should get approximately negative 78.48 meters, all right? Now here's the thing. It depends on what they're saying, but if they said how far, I'm thinking distance, which is the absolute value of your displacement, okay? And so you likely would not include a negative here because it's saying how far. How far typically is asking distance. It did not say anything about the direction, all right? It told you it was falling, so we already knew that. So if you did this, you could say it fell 78.48. We're going to get that to two significant digits in just a second, right? So that's kind of what you're going to think. If they said how far did it fall, then you're going to just list it as a positive because the falling piece indicates that it was a negative movement, all right? Two significant digits then. Two significant digits. So I need this digit and that digit. I'm going to say it fell 78 meters. It fell 78 meters. So a baseball player throws a ball straight up with an initial velocity of 22.8 meters per second. What is the maximum height that the ball will attain above the launch point? The maximum height that the ball will attain above the launch point. I know my initial velocity. In order for a ball to go up and come back down, this looks a lot like a parabola. We have a vertex. At the vertex of this parabola, it has 0 velocity. That is the turning point. That is the turning point, all right? And so the maximum height will always be at the turning point if you're throwing something up, all right? So we're going to say, well, how far? That answers the question, how far? We have a final velocity at the turning point, which is what we're talking about. We have a velocity of 0. We have an initial velocity. They have given us 22.8 meters per second as my initial velocity. I'm going to square that. On the bottom, I have 2 times gravity. Gravity is always negative here. 9.81 meters per second squared. All right? Meters per second squared. So you should get, when you plug this all in, what do you get? All right, so you should get 26.495. Keeps going. How many significant digits did we have initially? 3. So we need 3 significant digits, which is 1, 2. That means we round this guy. So it should be 26.5 meters upward is what you can say if you want to, right? But it went up 26.5 meters.